Okay, we'll take a look at all of the transformations you will encounter, but we're going to look at it as the as basics here. I'm not going to combine any transformations because in the long run you could do many transformations to what we call a parent function. Okay, so the parent functions such as y equals x squared, you should know the general graph of most of the functions you encounter. So knowing that a x squared looks like a parabola, right, from there I could investigate any form of a function x squared and know generally what that graph should look like. So there are different shifts or reflections and stretches and shrinks that can occur. First, let's look at what a vertical shift would look like. So in any website or your textbook, you'll see something similar to this for a transformation. And then there's all these rules. Okay, again, I'm trying to focus more on like, why is this the rule? What does it mean, right? Understanding the linguistics of algebra, breaking down even some of the definitions we do is tough. Okay, that's a challenge. So understanding the math behind it is more valuable than memorizing, thousands of formulas. So first off, a vertical shift. Well, if we took this y equals x squared and let's say every point here we moved up 2, okay, that's what I'm talking a vertical shift. I know my graph looks skinnier, that's not intentional. I'm freehanding these, and besides that, honestly, if you graph them, like say you use your graphing calculator or GeoGebra, sometimes your window may be misleading because it looks like maybe it shrank in some way or got skinny or whatever, but it really didn't. It's just your viewing window. Okay, so be careful of that. So this function I drew in green, it would look like y equals x squared plus 2. Okay, if I added 2 to x squared, it moved every point up 2. And you could verify that with if I did a table of values for y equals x squared, let's just do a couple here. That's what you would have for the original, right? But if I added 2, then the negative 2, 4 becomes negative 2, 6, right? If I substitute 0 is always a really easy one to check. If I substitute 0 in for y equals x squared, I get 0. But if I substitute 0 in here, 0 squared plus 2, I get 2. Okay, and that will happen along this entire graph. Everything got shifted up 2. So how does it get shifted down? Well, that's if you had, instead of a positive here, right, we had a minus. So let's say y equals x squared minus 3. Okay, it would still be this parabola. I'd take that entire parabola and I'd just shift it down 3. Okay, vertical is pretty easy. Add or subtract something to your function. And the parent function could be, a square root, or it could be an absolute value, it could be a cubic. Okay, any function that you have encountered, the basic one is our parent function. Okay, next, what would a horizontal shift look like? So first off, like on the graph, shift this entire parabola to left 2, or shift it to the right, 3 or whatever. That's a horizontal shift. So how do you know which one is which? Notice the formula has minus plus. It's backwards, right? Over here we had plus minus, here it's minus plus. The reason is this one is it is backwards when we look at the shift. If you would think, adding would move up or adding would move right. But in fact, to move to the right, it's a negative in here. And to move to the left, it's a positive. So why is that true? So as I said, often your zeros can help you see it, but when I say that, I sometimes mean actually what would give you 0, right? My original, let's use a highlighter here, 0, 0. If I substitute 0 in for x, I'd get 0 for y. Well, looking at the green, if I substitute -2 for x, I would get 0 for y. Right, so this x, y. If I substitute -2 for x, I get 0 for y. So that vertex of a parabola, that's the minimum or maximum point, right, that gets shifted left 2. Even though this is a +2, and the reason is, in the parentheses, to get this to be 0, I actually needed a -2. So horizontal shifts, the way I memorize these, it's backwards. Okay, and there's the reasoning why. And you could see with this x here, right, I would need x to be 3 to get y to be 0. Alrighty, there's horizontal shifts. Reflection about the x-axis. So to reflect about x means mirror image, right? It flips down here. So to get this mirror image, that's a reflection about the x-axis. It says y equals -f of x. What does that mean? So the original function is x squared. So we need now to take our function and make the whole thing negative. Well, again, I'm doing the basics, right? So I take the whole x squared and I make it negative. I get -x squared. A negative function will always reflect about the x. So to reflect about the y, it says f of -x. Well, how do we do that? Actually, really quick, to wrap this one up as well, notice if I said the original is f of x equals x squared, right? Function notation. But I want it to reflect about x. I could say negative, right? -f of x equals x squared. And to solve for f of x, I'll just divide by negative. So I'd have -x squared. Right? Same result, just a different way of looking at it with function notation. And I guess why that's important is because part D, it says if the x were negative. So in this one, we'd actually get the same thing. Okay, because if I make the x negative, so I have f of x equals x squared. And if I make the x negative and square it, right, then I'm right back to the original x squared. So remember, we've looked at symmetry. To be symmetric about the y, it says any of these x values, I'd get the same y value if I substituted -x, right? So that's exactly what's going on here. If your x is negative, then I just reflected about the y-axis. And again, the problem is if I make that x negative, let me just write y. If I make that x negative, right, if this were the problem, and I said graph that, well, you could just tell me, well, that's y equals x squared, right? Same thing. So even though I do have two different graphs, they coincide. They are the same graph. Okay. For this symmetry about x as well, we had looked at that with symmetry too, so just another way of looking at that. All right, vertical stretch and shrink. This one, these last two are probably the most confusing in my opinion, because one, you have to describe it correctly, but also sometimes they could mean the same thing. So let's take a look. First off, if I told you to double your x squared, take it 2x squared. Think of all the values you plug in besides 0, because you wouldn't really notice that. Whatever you get, right, if I plug in 1, instead of 1 originally, right, I'd get 2. So if I were to make a table looking at that original one, all of my values are actually twice as large. If I plug negative 2 in, out of 4 times 2 is 8. Negative 1 in, I would have 1 squared, so 1 times 2 is 2, and so forth. 0, 2, 4. Oops, 8. Okay, all of the y values doubled. Right? That's what it tells you, y equals double x squared. So what does that mean? That means that it's going to rise twice as fast. Okay, we call that a vertical stretch. Why? Because imagine grabbing this blue graph and stretching it vertically. Then what it would appear to do is look skinnier. Okay, that's a vertical stretch. And how many books authors describe this is that the absolute value of a is greater than 1. So why do they write absolute value? Because we don't care if it's positive or negative, right? I want to know overall this value here, is it larger than 1? And now why do I not care if it's negative? Because that's a different rule, right? If it were negative, it could reflect. So if I had y equals negative 2x squared, I'll do it in pink, I guess. Negative 2x squared would still be stretched, but then it's also reflected. Okay, that's how you could get more than one thing happening here. All right, and I need one more color because I just used my pink. So how do you do a vertical shrink then? So that one's a little harder to describe. Basically think of a number less than 1. Why can't say less than 1? Because what if it were negative, right? That's still less than 1. So we still use the absolute value. But again, you're just kind of looking at that coefficient of x squared. So like say we had y equals 1/2 x squared. That is less than 1. Okay, it's between 0 and 1. But even if you had a negative 1/2 x squared, it's still a shrink. It's just it's gonna reflect, right? So y equals 1/2 x squared. A vertical shrink would mean, picture that original blue graph, right? And pressing it down and shrinking it downwards. Think of like those funny mirrors, right? In haunted houses or whatever. Now, again, I could still set up a quick little t-chart to see. I'm not going to do all these values. Let's just do 0, 1, and 2. Substituting 0 would still get 0. 0 times 1/2 is 0. But substitute 1. 1 squared times 1/2 is 1/2. 2 squared is 4. Multiplied by 1/2 is 2. So all of these points, right, that were up here are now down here. Alrighty. So there's vertical stretch and shrink. So how about horizontal? So a horizontal shrink would look, let's do green, something like this. So what if I did y equals 2x squared? So notice in here it has they use c. It doesn't really matter what variable, what textbook, what website you look at. They may have a different variable there, but in this book we have c. So if I'm multiplying the x by some value, in this case 2, well then the entire thing is affected, right? 2x to the second. Horizontal shrink would mean take all the original values and shrink them, right? So therefore, I'm shrinking this way. But you could argue, well, that kind of looks like the last one, like that's a vertical stretch. Well, yes, a vertical stretch could look like a horizontal shrink. And in this function, the reason so, if we actually expanded y equals 2x to the second, we'd get y equals 4x to the second. And now that looks like a vertical stretch, right? Even larger than the last one. This thing should be even skinnier. That's why I didn't draw numbers here, like to tell you what the axes represent, trying to demonstrate the point. So we would shrink horizontally if the absolute value of c is greater than 1. Again, absolute value, because if that value x in here is negative, then that would be a reflection about the y-axis, right? That's separate. We're just caring about the horizontal stretch and shrink. So let's look at it. Shrink. Well, just like the vertical, if the c is between 0 and 1, so like y equals 1/2 x squared, right? Notice it's in the function, right? It's in the squared, it's in the parent function. So this comes out to be 1/4 x squared if we were to expand it, which is a vertical shrink, right? But it's also a horizontal stretch. Be careful of the way a question is asked, because although we are doing the same thing, if this were the problem, it matches the horizontal, right? And in fact, it matches the horizontal shrink. Even though we expand it, and I could say, I'm sorry, horizontal stretch, right? Because my bad. Oh, darn it. Just said it wrong out loud. It's stretched horizontally. We spaced it out, right? So even though we could expand it and say it's a vertical shrink, the way the original problem is written is this is a horizontal stretch. If the problem were written as it is here, then it's a vertical shrink.